Questions about other stuff? While you're thinking of your questions, there were 3 people who didn't submit either of the first homeworks, and they've been dropped from the class to make room for other people. There is a problem, though, in that the first roughly 8 people on the waiting list are waitlisted for sections that don't have room. So I kind of want to let the first people in first, but there's no section to let them into, other than letting them into a section that isn't their choice, which probably doesn't help since they have schedule conflicts, et cetera. So I'm a little bit stymied. If you are person number 1, 2, or 3 on the waiting list, come and talk to me after class. Other stuff you thought of? Okay, we were talking about kinds of data, and we're just leading into some of the sample data sets that we're going to be discussing as the course goes by. Some of these data sets come from scientific problems, some come from legal disputes and whatnot. The first data set comes from a trade secret case that I was involved in. This was a dispute between 2 computer hardware resellers. So they don't manufacture stuff, they sell stuff manufactured by other people. The short version of the story is that a couple of employees left a company, formed their own company, and within a matter of weeks were selling $1 million a month in hardware to customers of their former employer. And the former employer cried foul, said, "You stole our customer list. Customer lists are protected by law. They're trade secrets. Stop. And stop selling to our customers." And the new company, started by the former employees, their defense was basically to say, look, you guys are huge. Everybody is your customer. It was inevitable that our customer list would overlap with yours by as much as it did. It was basically unavoidable. We got the names not from your customer list, but from things that were readily available. We got them from CD-ROMs. We got them by looking at magazines to see who was advertising that they were selling the kind of equipment that we would be supplying them with, so forth and so on. So that's basically the nature of the dispute. And the question, the statistical question is, well, was it really inevitable that the overlap in their customer lists would be that large, or was this somehow surprising if they were behaving innocently? And we'll talk in detail about how to test the hypothesis that, in some sense, the overlap of the lists is what you would expect if they were selecting customers blindly from these universes at random, which is not really a tenable hypothesis, but it gives you some idea of whether things were inevitable or not. Meanwhile, we're going to introduce the data because we're going to be looking at the data, just an opportunity to talk about how to display things. So the legal background is the following, that an affirmative defense to being accused of stealing a customer list is that if the list is readily ascertainable by proper means, then you're clean. So if the defendants can convince the finder of fact, that's the judge, that it's virtually certain that anybody who manufactures certain types of products uses, in this case that's serving as the precedent, rubber rollers, that the manufacturers of those products are easily identifiable, and that the defendant's knowledge of those plaintiff's customers resulted from that identification process and not from the plaintiff's records, then the defendants have an affirmative defense to the misappropriation claim. Okay, so here's the data. The original company, WBH, had 3,310 active customers. The new company had 132. 93 of those they shared in common. The new company claimed to have found the names of 27 of their customers in trade magazines and 31 from CD-ROMs. There were a total of 469 potential buyers. Okay, this is utterly impossible to read, right? Okay, this is not a good way to display data. That's the point, all right? So this is a much easier way to understand what's going on. So just to look at it, how many customers are there in the world who buy this kind of stuff? That's this cell. So there's more than 90,000. Everybody conceded that there were more than 90,000. 3,310 of them were customers of the first company at the time in question. 132 of them were customers of the new company. They shared 93. How many of those were outside the Bay Area? I'll mention in a little while why that matters. But there were more than 60,000 outside the Bay Area, of whom 1,769 were customers of the first company, 8 were customers of the second, and all 8 they had in common. How many customers are there on the CD-ROM? At least 90,000. They conceded that all their customers were on the CD-ROM. I don't know whether anybody actually checked. And they claim to have gotten 31 from the CD-ROM by looking at people who sold this stuff. Of those, there are 22 that they share in common. How many had advertised in trade magazines? There were 469 in the trade magazines that were brought into evidence. Of those, that included 152 customers of the first company, 27 of the second. 26 of those 27 were shared. All right, so why does it matter if they're outside the Bay Area? What matters is that if you're outside the Bay Area, it generates a phone record if you call them. So if they were analyzing each other's phone bills, or at least the plaintiffs were analyzing the defendant's phone bills to see who they were calling and who they were calling most. And the overlap, was large. Those that would generate phone records, a very large number of them were in common. So the non-local customers. So of the 53 that were shared, the phone calls made, there were 1,006 phone calls made that would have generated a record made by the second company out of a total of 1,050 phone calls they made that would generate a record on their call. So the vast, vast majority of phone calls that they made that would generate some kind of record on their phone bill were made to customers who were customers of their former employers. All right. Okay, these data are quantitative. They're discrete because they're counting things. We'll talk about that a lot. You should make sure that you know how to read tables. These are examples to get you there. Any questions about just the idea of displaying data in tables as sort of a crosstab? Go on and talk about a rather different data set. This one comes from physical science problem. This is measuring the acceleration due to gravity. You guys remember from, how many of you took physics in high school or otherwise? Many? Okay, you drop stuff, it falls, right? It goes faster and faster and faster. The acceleration due to gravity is roughly 9.8 meters per second squared. But that's roughly, and it actually depends on where you are, because if you're standing over a particularly dense part of the Earth, that's going to attract things more than if you're standing over water, for example. I mean, there are variations in the acceleration due to gravity that have to do with what you're close to. Moreover, the Earth is shaking all the time from earthquakes, from tidal motion, from waves pounding on the beach, and every time things go down, it's sort of, that's almost as if you get a little bit lighter, and if things come toward you, you're sort of accelerating towards the center of the Earth faster. So there are very small variations in gravity that are useful for doing things ranging from understanding the tectonics that lead to earthquakes to exploring for oils and minerals. All right, so this instrument, most measurements of gravity that are done on the Earth for exploration for minerals and whatnot are relative measurements. They sort of compare the acceleration of gravity in one place to the acceleration in another. And it's a very difficult thing to measure gravity on an absolute scale, to get a number rather than a difference between one place and another. These scientists built a very elaborate instrument that measured gravity by dropping a reflector in the path of a laser beam. And you guys know that about interference fringes, that you have things that add in phase or out of phase. So as this reflective cube falls, you get constructive and destructive interference of the laser light wave as it goes down, and they can count the interference fringes. And they know the wavelength of light of a laser very, very accurately, so they can basically measure where the cube is as a function of time very, very, very accurately and figure out how rapidly it is accelerating. Now, because they're trying to get incredible precision on this, not only are they measuring it in a laser, but they're dropping this thing inside a vacuum chamber so that it doesn't bump into any air molecules. And then just in case there are any air molecules left in the vacuum chamber, there's like this thing that goes down, a cage around it that goes down at approximately the right rate so it'll knock any of the air molecules that are left out of the way. I mean, it's just a really remarkable instrument to measure things to phenomenal precision. Right, so it's, what we're going to look at are data that are deviations. They're the difference between the measured acceleration due to gravity at this particular place and a reference value. The reference value is this 9.792838 meters per second squared. All right, so here are 100 measurements of the acceleration due to gravity. It's the difference between the acceleration and that reference value multiplied by 10 to the 8th. Okay. What's 10 to the 8th in words? 10 to the 6th is a million, 10 to the 7th, 10 million, 10 to the 8th, 100 million. Okay, so these are multiplied by 100 million. Yeah? Okay, so these are put in a table, but the table doesn't mean anything, right? This is just a convenient way to display. It's not like the table we were looking at before where a row meant something and a column meant something. These are just laid out in a square. All right, looking at this, I have no idea what's going on, right? This is not a very convenient, this is not a very illuminative way of looking at the data, okay? It doesn't help us learn things. So we want to figure out how can we take some large set of observations like this and actually get some intuition for what's going on, right? I mean, can you tell even at a glance whether most of those numbers are positive or negative? I think they're kind of mostly negative, but do they average to 0? All right. So I'm going to gloss over why anybody would want to make so many measurements. You can look at it yourself. We're going to look at summarizing the data a number of different ways. The first is in a table that helps us make some sense of it, and then we're going to look at graphical ways of summarizing it, histogram in particular. So one way to try to take this long list of numbers and get some idea of what's going on is to divide it into ranges and count how often there are values in those ranges. So we could divide this range of values. It turns out minus 160 is smaller than the smallest value in the list, and plus 160 is bigger than the biggest value in the list. So we divided this into ranges that include every observation. All right? What else do we want? We want these ranges not to overlap. They need to be disjoint ranges. We need to have some endpoint convention that says if I get an observation that's exactly minus 160, does it go in this bin or not? If it's exactly 110, does it go in this bin or not? So this says this is going from minus 160 to minus 110 inclusive. So if an observation is exactly 110, it goes in this bin, not in this bin. Even this one starts at 110, but it starts with sort of an open, you know, in math notation, this would have a curly paren on the left-hand side and a square bracket on the right-hand side. Okay, so we divided things into ranges, and now what we're going to do is make a frequency table by figuring out what percentage of the observations fall into each of these disjoint ranges. These ranges are called class intervals. They'll also be called bins. Okay. All right, so how do we do that? Well, it's going to invite error to try to do it from the raw list, because you're going to go through and you're just going to misclassify something as something else. So it helps an awful lot to sort the list first. So if we sort the list into increasing order, then we can pick off pretty easily how many observations are in that first class interval. The first class interval was minus 160 to minus 110. So we go, this is bigger than minus 160 and less than minus 110. On up to here. Then this one is in the next bin. Okay, so the first 9 observations are in the first bin after you sort them. So these are those 9 observations. 9 out of 100 is 9%. So our entry in our frequency table for that class interval will be 9%. All right, so this is basically, this is showing a frequency table. The first bin from minus 160 to minus 110 has 9% of the observations. The next bin has 10% of the observations, and so on. So let's just do this one, 50 to 80. I mean, this is kind of mindless work. But just for the sake of argument. OK, so which observations are in that bin? Yeah, it's just these two, right? OK. So 2 out of 100 is 2%. Now, this is a reason to do this. If I put in the number 2, is that a right answer? No, it's 2%, right? So in your homework, oops. Where did it just go? I went on to the next entry blank instead of... OK. So in your homework, you need to pay attention to whether there is a percent sign after the answer or not. If there's a percent sign after the answer blank, it's going to divide your answer by 100. It's going to turn it into a percentage. OK? If there isn't, and the number that you're trying to put in is 2%, you better put a percent sign after it, or you can put in 0.02. 0.02 is the same number, right? So 2% is 0.02. OK, so that's still a right answer. Now, something to be aware of is when you are working on problems in the book, that's still a right answer. But if you submitted that as part of your homework to the server to grade, the server will not know how to divide 2 by 100. OK, so what happens in the book is different from what happens in the homework grading. Is this? Yes?
So what's accepted by the homework grading?
A number. If it asks for a number, you need to put in a number rather than an arithmetic expression. 0.02 or 2% would be fine. 2 divided by 100 would not. OK, so here, 1 divided by 100 is going to be wrong, but 20 divided by 1,000 is going to be right. But if you submitted it for your homework, it would be wrong. It's looking for a number, not an arithmetic expression. OK. OK. All right, so here we've got now a frequency table. This helps a little bit. We kind of summarize things. We can see what the percentages are in various ranges. That's helpful, but it's really still not that great a way to get a gut impression of how the data are distributed. I mean, are big values common or small values common? What's a typical value? How spread out are these things? So forth and so on. So what we're going to do next is a graphical representation of the frequency table, which is a histogram, which many of you have seen, although there may be a little bit of confusion around that. So I've made this so big that it no longer fits on the page. Let me shrink it just slightly. All right. So the way we make a histogram, it's this series of rectangles, right? And the area of each little rectangular bin is what matters. So the area of that bin is going to represent the relative frequency of observations in the range. So in this particular case we're looking at before, what we're going to do is we're going to have a bin. The base of the bin is going to be the range -160 to -110. That's the class interval. And then the area of the bin is going to be 9%. Not the height, but the area. Okay, so this is normalized to area. Area is what matters. So the area of the bin is the fraction of data that are in the bin. So that's the number of observations in the class interval divided by the total number of observations. So if we want to figure out, well, how tall do we make the bin so that it has that area, you just flip things around algebraically. The height of the bin is going to be the fraction of data that are in that class interval divided by the width of the class interval. So here's a cartoon. The units on the vertical axis are what's called a density scale. The units are percent per whatever's going on in the x-axis. Why is it percent per that? Well, because if you take this number, percent per unit of that, and multiply it by that, you get percent. Right? So just sort of a dimensional analysis tells you that if you want to end up with the area being percent, and this has some units, then the units of this has to be percent per that. Does that make sense to everybody? OK. So the area of the bin is proportional to the relative frequency of observations in the bin. The height of the bin is the relative frequency divided by the width of the bin. All right. So if we want to make a histogram of the gravity data using those same class intervals, remember the first class interval went from minus 160 to minus 110, and it had 9% of the observations. So we've got 9, what's the height of the bin going to be? Well, we want the width times the height to be 9%. So the height is 9% divided by the width. Okay, what is the width? The width is the upper endpoint minus the lower endpoint. The upper endpoint is minus 110. The lower endpoint is minus 160. Right? Minus 160 is smaller than minus 110. So the width is 50 measurement units. What are the measurement units? Measurement units are 10 to the minus 8 meters per second squared. Okay, that's okay. So far, so good? Okay. A reason for doing this with such crazy numbers that have 10 to the minus 8 in them and whatnot is so that you learn to keep track of that stuff, because it actually does matter. Now, you will very often see things that people claim are histograms but are in fact bar charts instead. In a bar chart, it's the height of the bin that matters, not the area of the bin. And typically in a bar chart, all the bins have the same width. If they all have the same width, there's really no difference between the area and the area is proportional to the height, right? Because the widths are all the same. It doesn't matter that much. But you'll often see things where you have little rectangular areas and they're separated from each other. They're not all connected. That's a different thing. A bar chart is different from a histogram. Okay, here is a histogram of those pinion flat gravity data where the bases of these bins are the class intervals that we used in the frequency table before. Okay, so this is the range minus 160 to minus 110. And there's scroll bars down here that let you select part of the area. And if we go from minus 160 to minus 110, we've selected this bin, and we can read off in microscopic font that won't show up on TV that the selected area is 9%. Okay, so we can read the area off this. Now, what fraction of observations are between minus 160 and minus 140? Well, if I go here from minus 160 to minus 140, this says that 3.6% of the observations are in that range. Is that right? Can it possibly be right? How many observations are there? 100. What's 3.6% of 100? 3.6. Could there be 3.6 observations in that range? No. Okay. When we bin the data to form a frequency table or a histogram, we lose information about where in the bin the observations are. I know that there's 9 observations in this whole range from minus 160 to minus 110, but I have lost the information about where in that range those observations are. Okay? This bin starts at minus 160. Does that mean that the smallest observation is minus 160? No. It means that the smallest observation is somewhere in this range between minus 160 and minus 110. Okay. So from looking at a histogram, you can't tell what the smallest observation is, what the biggest observation is. You can't tell exactly what fraction of observations are in any range other than the bins. Okay, for a whole bin, I know that it matches exactly. I know that there are 9 observations between here and here. But I don't know how many there are between there and there or any part of this. Okay? I know how many there are between minus 160 and here. That's going to be an exact number. But anything else is going to be an approximation. Does that make sense? Information is lost. All right? It's a one-way trip. But we get a lot better feeling for what's going on with the data by looking at this picture, right? We now see that confirming what we saw by eye, most of the observations are indeed negative, right? They're kind of spread out. Looks like large positive deviations are, you sort of get further away on the right than you do on the left. This would be an example of something that is skewed to the right, has a long right tail. That's a description of this. This has one mode, unimodal, one bump. Okay? This is a unimodal histogram. It's skewed to the right. It has a long right tail. Okay? Let's talk a little bit about skewness and what kinds of things tend to be skewed. So what are things, so I'm not sure if I'm getting across the impression clearly, but the idea is the bulk of the observations are in some range, and then every once in a while you get something very far off in one direction. It doesn't happen in the other direction. Okay, it's not, all right. So things like how many years it takes to get a PhD in history, right? Would that be skewed to the right, or would it be skewed to the left? Okay, so most people would take, what would you guess, to get a PhD in history, for the sake of argument? 6 years, maybe? 5, 6, okay. And then there's that guy who's been working on his dissertation for 20 years, right? Okay, so he's way out here. Okay. Does anybody get their PhD in a month? No. Okay, so there's sort of a wall on the left-hand side that keeps the observations from getting too small, right? But they can go out in the right direction kind of indefinitely, and they do. All right? A lot of other things have distributions that are skewed to the right. House prices, prices of almost anything tend to be skewed to the right. Now, you go somewhere like the Bay Area, there's a median house price, which is lower than it was a year ago. But it'd be very difficult to buy a house for less than, for the sake of argument, $300,000 in Berkeley. I'm making up the number, but it's probably not horribly inaccurate. Okay, so there's in some sense a minimum price. I mean, maybe you can find something that needs a new foundation and is completely eaten by termites for $100,000, but it doesn't kind of drift off to the left indefinitely. There's kind of a hard bound. On the other hand, and then probably most of the houses are between, for the sake of argument, $400,000 and $1 million. But then, there's some houses out on Grizzly Peak that are 10 million bucks, 15 million bucks, whatever, right? So you have a very, very long tail going off to the right. That's an example of something skewed to the right. Can somebody think of another example of something skewed to the right? Yes? Income. Okay, very few people make less than 0. Well, some of us do. I mean, if your expenses exceed your income, you're negative net income. But we'll talk about salaries, maybe. So salaries are typically positive. You don't pay to go to work. Anybody? I mean, you guys want to be econ and business majors and so forth and so on. Do you have an idea what salaries are like typically? What median salary is? What 90th percentile is? Something like that. 100? Oh, I don't mean for starting salaries as economists. I mean in the U.S. for the sake of argument. Yeah. So looking at our population, just general statistics. 40, 50,000 is kind of what people are saying is kind of median. That our guess. What would you say? What would you guess is? We haven't talked about percentiles yet, but everybody knows that from standardized testing. So, what would you guess the 99th percentile to be? We get a very distorted view in the Bay Area. Do you think it's over 1 million? No. Okay. Maybe a couple 100,000. Maybe 300. No, 99th. All right. Okay. Well, and then there are people who get truly astronomical annual payments for their job. I don't know whether you want to call them a salary or not, but sort of salary plus bonuses, can be hundreds of millions of dollars. They can be really outrageous. Okay, so that's something that's very much skewed to the right. Not a lot of people have that kind of work. Yes?
For all those outliers, would there be, for the $10 million house, would there be a blank between the last, $800,000 house and that one, or would the range be adjusted so there's always a box?
Okay, so the question is, if you look at a histogram, do you always draw the histogram in such a way that things are kind of filled in the middle rather than having kind of an area where everything's 0 and then something bumps up at the $10 million house? And the answer is, drawing histograms is a bit of a black art. There are guidelines on how many bins to use. When you get into the tail where the observations are rare, it makes a lot of difference how many bins you use because the visual appearance can be quite different. There's no rule that says you must do it this way, but you do need to be aware when you do it that the visual appearance will change as you change the number of bins and locations of the bins. And we'll actually can look at that in a second. Another question?
Yeah, I wanted to give another example. What about the weight of people's weight?
People's weights. Okay. That's a very good example of something that is skewed to the right as well. Right? You're not going to meet a lot of people over the age of, let's say 15 who weigh 50 pounds or less. Okay? But you will occasionally meet somebody who weighs 500 pounds, 600 pounds more, right? So you're kind of backed up against this wall that there's kind of in effect a minimum weight. Most people, weigh something in some range around that, and then occasionally there's an extreme observation. There's a small fraction of the population that is very far away. It's a long right tail. Yes?
I just wanted to make one point about what his question was, because once you make that bin size, though, you've lost all the information about the fine detail in there, as Professor Stark mentioned earlier, so you wouldn't see gaps, even though maybe there was no one who made between 800,000 and a million or something like that. You wouldn't see gaps if you made your bin go from, say, 400,000 to 2 million. And that's what you use that information.
So here's an example. If I drew my histogram with a lot of bins, I might have a bunch of bins that are empty, and then these would be filled, which I think is what you were talking about, right? So in this case, I've chosen the bins to be so narrow that I basically have about, well, in this case, maybe 5 observations in this bin, but typically it's 1 observation per bin. Yes. So I've lost less information, but it's also less helpful. Okay, it looks kind of ratty. All right. Anybody think of an example of something that's skewed to the left? Excuse me. Yes? Laptops. The weights of laptops, or what the price of laptops? I'm not sure. So I think the weights might well be skewed to the left, but I'm not sure that the prices are. I mean, you can get a laptop that weighs a little under 2 pounds, and most are in the sort of 5 to 7 pound range. And it's been a while since the 12-pound behemoths were very popular. But the prices, I think, are probably skewed to the right. But I don't know. It's possible. I don't have a clear vision. Another example? Yeah. GPAs. You can't go higher than a 4.0. There's a self-limiting thing that keeps you from getting too much below a 2.0 for very long.
How about incoming GPAs from high school?
Incoming
GPAs for high school students entering UC Berkeley.
Incoming GPAs for high school students entering UC Berkeley. We have a refinement of the thing. That sounds, yeah. How would you get in with a microscopic GPA? Yeah. It happens, but it doesn't happen that often. Okay, one way to construct things like this is to turn right-skewed things on their head, for example, in the following way. You think about what fraction of a family's income is spent on food. Okay. Sorry? Yeah, there's only so much you can spend on food, even if you have caviar for every meal, right? And fly to Paris for dinner every Friday, or whatever it is. There's still a limit, right? So those people who make an enormous amount of money are the people who spend a microscopic fraction of their income on food. And so we sort of turn this thing around by looking at it at a fraction of a bigger and bigger base. Does that make sense, everybody? Okay. All right, let's talk. Actually, let's take a minute to stretch our legs and then come back. it's one more step beyond. Yeah, okay, thanks. Okay, let's start again. There was a good question just now about one of the homework problems, so I'll give you a little freebie because reasoning is due tomorrow, right? Yeah, okay. So there's a question that basically says something like the premise is not A or B, and so that's and the question is it valid to deduce from that not A or not B? Okay, and what one of De Morgan's laws tells us is the negation of A or B is not A and not B, right? Okay, so from this, these two are logically equivalent, right? This implies this implies that. That's really the same thing, okay? Does that mean that this doesn't imply that? No, does this not mean what? But okay, okay. If it's true that A is false and B is false, then is it true that either A is false or B is false? Okay, if A is true and B is true, then A is true or B is true, right? Because A or B is true if either A is true or B is true or both. Okay, this is saying both both A is false and B is false. Therefore, either A is false or B is false. Because this is true if either A is false or B is false or both are false. This is saying they're both false. Okay, so this is a two-way street. Not A or B is logically equivalent to not A and not B. These are not logically equivalent, right? If this is true, it doesn't follow that this is true. But if this is true, that has to be true. Okay, so this is a one-way street. Okay. Okay, so that's a valid argument. If this is true, that's got to be true.
So the top's true and
Sorry?
the ones on the left, that's true and that.
This implies that. That's a valid argument. Yeah. Okay, let's find where we were. Okay, percentiles, quartiles, median, so forth and so on. The way that I define this stuff might be different from what you have seen before if you have taken statistics before. So this is a caution point where my definition might be a little different from the definition that you've seen. You better use my definition when you're doing the homework in the final. When you go forth, all that matters is that you are clear on which definition you're using. But if you want to get a good grade, do it my way. All right, so percentiles, what is a percentile? The pth percentile of a list is the smallest number that is at least as big as p% of the entries in the list. Okay, so let's do an example because that's kind of easier than trying to talk this out. What is the first percentile of this list? Okay, it's the smallest number that's at least as big as 1% of the elements in the list. These are sorted into increasing order. The smallest element is this. There's 100 of them. So minus 152 is the smallest number that is at least as big as 1% of them. Okay. The second percentile would be minus 132. That's the smallest number that's at least as big as 2% of the elements of the list. What is the 2.5th percentile? Well, what's the smallest number that's at least as big as 2.5% of the elements of the list? Can you be bigger than exactly 2.5%? No. I'm sorry. So three numbers are in fact less than or equal to minus 132. So minus 132 is the smallest number that's at least as big as 2%, 2.5%, and 3%, right? So that's what you're telling me, and that's correct. So I'm okay. So in fact, 3% of the numbers are less than or equal to minus 132. That is the smallest number that is at least as big as 2.5% of the data as well. So the 2.5 percentile of this list is minus 132.
Is it because it's a coincidence because both are 132, or because one is 2.5, you go to the third one? So let's do 3.5.
Okay. Let's do 3.5. What would the 3.5 percentile of this list be? It's the smallest number that's at least as big as 3.5% of the numbers in the list. Okay? To be bigger than at least 3.5%, you in fact have to be bigger than 4%, bigger than or equal to 4%, right? Because, okay, so the 3.5 percentile of the list is minus 128. That's also the 4th percentile. It's also the 3.9th percentile, 3.8th percentile, et cetera. But the 4.00001th percentile is minus 122. Okay? So we're talking about the smallest number that's at least as big as a given fraction of elements of the list. Now, where you're going to say, but that's not what I learned in high school or my other statistics class or whatever, comes to there's an even number of, so some percentiles have special names, right? There are deciles, there are quartiles. Deciles are 10%, 20%, 30%, et cetera. Quartiles, 25th percentile, 50th percentile, also known as the median, 75th percentile. The 25th percentile is sometimes called the lower quartile. The 75th is sometimes called the upper quartile. 50th is called the median. This list has 100 numbers. What number on the list is the median? Okay. It is the smallest number that's at least as big as 50% of the numbers on the list. That would be the 50th number in the sorted list. Some of you learned somewhere that you should average the 50th and the 51st numbers to make the median. That's a convention. There's nothing wrong with it. It's just not how I do it. Okay? So it's the smallest number that's at least as big as 50%. So that's the 10th, 20th, 30th, 40th, 50th. So the median of this list is minus 47. Okay? All right. Now, to figure out what a percentile is of a list of numbers, you need the list of numbers. If you condense the list of numbers by making a frequency table or a histogram, you've lost information about where in the bin, where in the class interval the data are. So you can no longer exactly recover a percentile once you've made a frequency table or a histogram, but you can still estimate percentiles from the histogram. So how would we go about estimating? Let's take this back down to a sane number. All right, this is now a histogram of the gravity data done with 9 equal width bins. So it's a different histogram, different class intervals than we were looking at before. There's no particular reason to use 9. That's just what I happened to pick. Okay, here I've selected the range from minus 152 to minus 44.2. And we read that the area of that selected range is 50%. So my estimate of the median from the histogram is minus 44.2. That's the smallest number so that the area of the histogram up to that number is equal to 50%. All right? It is not the median of the list. Right? The median of the list was minus 47, we just figured out. Right? This is off by a little bit because it knows, the histogram has sort of built into it the right number of observations from here to this edge of this bin. But in this bin, all we know is that there's a certain number of observations in there and all, but we don't know quite where they are. And what the histogram is doing is pretending that they're sort of evenly smeared out in this entire range. So when we find the area of part of a bin of the histogram, we're just finding a fraction of the area of the rectangle as if the data were evenly distributed within the rectangle. But they're not. They're distributed however they are distributed. Okay, so we end up that our approximation to the median that we read off the histogram by finding the area is only an approximation. In this case, it's pretty close, but it's not going to be the corresponding percentile of the original list in general. Might be by accident. All right. So let's find an estimate of the lower quartile, the 25th percentile from the histogram. So what do I want to do that? Okay, I want to fiddle with this number until this is 25%, right? Okay. So I'm going to need to make it smaller, yeah? All right. How do I make negative 44 smaller? Not by changing it to negative 20, I think. All right. So I went a little too far. Oops, wrong way. Okay, so minus 79.5 would be our estimate of the lower quartile from the histogram. Okay? The actual lower quartile is something else. What is it? We need to find the smallest number that is at least as big as 25% of the observations. So there's 10, there's 20, 1, 2, 3, 4, 5. It turns out to be minus 80. Okay? Just off by a little bit. Okay. Down one more. All right, now, just I'm saying it over and over again because you're going to get this wrong on the homework, some fraction of you. Can I tell what the largest number is in the data from looking at the histogram? No. Okay, good. Can I tell what the percentiles are from looking at the histogram? In general, not. If it happens to line up with the boundary of a class interval, yes, but generally, no. Okay? Typical cases, no. All right. This histogram applet, when we first saw it, didn't have a lot of controls. It's getting more controls now than it did before. There's now a box that lets you change the bin size. There's this list data button. And then there's this additional information. N is the number of observations. This is the mean of the observations, the standard deviation of the observations. We'll get there in the next chapter. If I click the list data button, it should bring up just those are the data. Okay. Later, there's going to be summary statistics as well. What I try to do in the class is the tools get more features as you get the concepts that go with the features. So they start off being relatively simple, and then they get more bells and whistles as we learn more. All right. Questions about any of all of these things? Wow, did we talk about all that? Yeah. Okay. Yes?
You know how you said for the endpoints when you figure out the range, how you determine whether they are inclusive or exclusive?
So the question is, when you're setting up the class intervals for making a frequency table or a histogram, how do you figure out whether to make a particular endpoint inclusive or exclusive?
The question was going to be, why don't you make them all inclusive?
Oh, because you answer your own question. Okay. All right. So the question that you would have asked was, why not make them all inclusive? And the answer is because then you don't know which bin to put one in that falls on the boundary between two if you're supposed to include it in both. So, okay. All right. Other questions? No more questions. All right. So now you are equipped to do the homework that is due on Monday. Yes?
I have a question. In general, should we be reading these before and then listening to your lecture? Should we be doing the reading after?
So the question is it better to read before you come to class or listen to the lecture and then read after? If you read ahead of time, you will learn more and you will probably be more bored. So I don't, there's a trade-off, right? If you read it ahead of time, you can come to, you can use class as an opportunity to clarify some of the things that were a little fuzzy when you read through it. You will have already been, sort of primed to the material. I think that that's the way to learn the most. That said, it might not lead to the best user experience. So I'm not sure what to tell you. But you know, the diligent students among you will read first and then come to class and ask questions.
Will we in general do like one chapter a lecture, or will we do like 1.5?
Question, do we do a chapter lecture, more or less? And I intend to cover roughly a chapter a lecture. There are some chapters that take a little longer. There's some that will go a little bit faster. Now, the homework problem with the histogram that goes with the chapter we were just working on, and the one that goes with this chapter, I just upgraded my laptop to Snow Leopard, the latest version of the operating system, and some stuff no longer works that used to work. So there's a possibility that there's going to be some technical glitches depending on what operating system you're using, what browser version you're using. Again, stuff that used to work with Firefox 3 is not working as reliably with Firefox 3.5. If something looks weird, let me just show you an example here. If I can go to the right window. It shouldn't look like that. That's Firefox 3.5, and those colors do indeed exist in the applet for displaying the overlay of various things with each other, but I don't know why it's coming out like that and it doesn't look right. So if you get something odd, you should ask me, ask Mike, ask a GSI, ask somebody to make sure that what you're seeing is what you ought to be seeing. Well, the colors are not the colors that they're supposed to be, for one thing. What's really weird, like that's showing half the histogram. If I scroll a little bit, it jumps around. I mean, it's just not behaving well in Firefox 3.5 under Snow Leopard. It was behaving just fine under Leopard with Firefox 3. Well, that's what it ought to look like, but it ought to be centered. Okay. Your mileage may vary. All right.
My laptop will always be in drop-in tutoring, so if you need to check something, I will be there.
All right. Okay, so we've just talked about taking, a verbal description of data and making it a little bit clearer or easier to read by putting it in a table. We've talked about taking lists of numbers and trying to make sense of them by reducing them to frequency tables or to pictures, histograms, in this sort of direction of reductio, reducing things, right? What's the farthest you can go? Well, you can reduce an entire data set to one number, right? One single number to summarize the whole thing. Well, what's that number going to be? Well, you'd like to summarize the data with a number that represents the whole list in some sense. What number best represents the whole list? Well, it depends on what you mean by best. Okay? And different definitions of what it means to be best lead to different one-number summaries. So a one-number summary is typically called a measure of location. It tells you what's typical for the data. And we're going to talk about three measures of location: the mean, the median, and the mode. And they are all the single number that best represents the data for three different definitions of best. Okay? So the mean, in what sense is the mean the best representation of a list of numbers? Well, the mean is the number that is closest to every element of the list if the way you measure distance, the way you measure closest, is by taking the square of the difference. Okay? So the mean is that number, so that if you take the difference between that number and every element of the list, square those differences, add them together, you get the smallest value. It minimizes the sum of the squared deviations. Okay? And you can prove this by just a little bit of calculus, which we're not going to do. But all right. The median, right? We learned last time the median is sort of smallest number that's at least as big as half the numbers in the list. That minimizes the distance between, that has the smallest average distance to every element of the list. If instead of measuring the distance by the square of the difference, you measure by the absolute value of the difference. Okay, so it's very, very similar, very analogous, but you're measuring distance by absolute value instead of by square. Right? the mode, it does the best job of measuring distance if you basically say, if you match, the distance is 0. If you don't match, the distance is 1. So you just sort of count hits. Okay? So the mode is the most frequent value. A list can have more than one mode. So if you have a list that's 0, 1, 2, 2, 3, 4, 4, 5, 6, then did I say 2 twice and 4 twice? 2 and 4 are both modes. Okay? If you count how many observations are not equal to 2, you get the same answer as you get if you count how many observations are not equal to 4. Okay? If you count how many observations are not equal to any other number, whether it's on the list or not, you get a bigger answer. So the numbers 2 and 4 are modes of the list. They minimize the number of numbers that are not equal to them. Okay? Just counting those that aren't the same. All right. Okay, we can relate all of those numbers to the histogram, loosely speaking. The mean is roughly where a histogram would balance. If you imagine carving the histogram out of a block of wood, the mean is the balance point. Now, it's not going to be exactly that because we've lost detailed information about where the data are when we binned them to make the histogram in the first place. But loosely speaking, it's the balance point of the histogram. The median, we talked about how to relate that. Excuse me, dumping trash on the floor. We talked about how to estimate that from the histogram. It's roughly where half the area is to the left and half the area is to the right. The mode is the biggest bump in the histogram. Now, depending on how many bins you use and where you put the bins, that biggest bump can move around. So this is just qualitative idea, right? But that's the right flavor. All right. I'm not going to take you through calculating this stuff. I'm going to trust that you guys are perfectly good at doing arithmetic. But let me talk a little bit about summaries of this stuff. Let me inflate the screen for those of you in the back, including the camera. All right, so the mean and the median don't have to be close together. If the distribution of the data is symmetric, if the data are not skewed, if the list isn't skewed, then the mean and the median are the same. It's the balance point, and it's also the place where 50% is to the left, 50% is to the right. If you have a skewed distribution, if it's skewed to the right, those observations that are way off to the right, when you square their difference from something, the square has more influence than the absolute value of the difference. The square grows faster than the absolute value. What's the effect of that? It's going to pull the mean to the right. If you have a distribution that's skewed to the right, the mean is going to be bigger than the median. If you have a distribution that's skewed to the left, those extreme values on the left have more leverage on the mean than they do on the median. They're going to tend to make, they will make the mean smaller than the median. But this is very much like being on a seesaw, right? If a small child can balance a full-grown adult if the adult sits close to the fulcrum and the child sits far away from the fulcrum, right? So even a little bit of mass sort of way off in one direction can balance a lot of mass. Okay, all right. Now, there's a notion in statistics that is useful to think about when you're doing data analysis, the notion of resistance. And so a statistic is something you compute from data. Right? A statistic is resistant if by changing one or a small number of observations, you can't change the value of the statistic very much. If by changing just one observation, you can make that statistic take any value you want, then the statistic isn't resistant. Okay, the mean is not resistant because if I take one observation and make it enormous, I can make the mean as big as I want. If I take that one observation and make it enormously negative, I can make the mean as small as I'd like. Okay, so by changing just a single observation, I can manipulate the value of the mean. I can alter the value of the mean. It's not resistant. The median is resistant. If I take a big observation and I make it bigger, that doesn't change the median at all. 50% of the observations are still, the midpoint stays the same. If I take a small observation and I make it smaller, that doesn't change the median at all. If I take something and cross the line from being below the median to above the median, I can move the median by as much as the distance between the observations that bracketed it, but I can't move it arbitrarily far by just changing one observation. Is that make sense to people? Okay. The mode is not resistant typically. Well, the mode might or might not be. It sort of depends on how many observations are shared, how many values are in common. If you have something where every number is equally frequent, then you can sort of move move one number to double up another, and that can move the mode a lot. But we're not going to worry about that too much. Okay. It makes a difference what measure of location you use, and you need to think about what the goal is of looking at the data that you're looking at. What question are you trying to answer? And one of the ways in which statistics can be manipulated to affect public opinion, to win an argument, whatever it is by judiciously choosing what measure of location to use to summarize a list. Okay? So for some purposes, the mean really makes sense and the median really doesn't. And for other purposes, it's the other way around. So if I want to know whether home prices in the Bay Area are higher on average, and what I mean is in summary, than home prices in Austin, Texas, for the sake of argument, then what's the relevant, what question do I really want to know? I want to sort of know what's a typical home price. What is the right measure of a typical home price? The arithmetic mean, sort of the average, or the median? Which one's a better measure? Did I say arithmetic mean or the median is what I meant to say? I'm not sure that's what I said. Okay, so the median, okay, so the median says half the houses cost less than this, half cost more, right? So if I want to know, typically, can I afford a house in Austin, the median is going to be more informative than the mean. The mean might be heavily driven by the price of Michael Dell's house, okay? So the mean, adding up all of the home prices and dividing by how many homes there are, the average number of dollars that a house costs, the average number of dollars per home, is not as informative about what's typical for the cost of a home as the median. Okay? But if what I care about underneath is somehow, a total, if I want to know like, per capita, I'm trying to think of a good example. I probably have something here. You don't know how much money a family can afford to spend on housing. That's related to the total income in the family, right? So the median income of family members in this one particular family doesn't tell me a whole lot about how much money that family has. The mean is much more informative. It's the total number of dollars that the family makes divided by the number of people in the family. So the mean is closely related to the total. It's the total divided by the number of things. So when the total matters, the mean is a more relevant measure. All right. Here is a canonical example of an opportunity to play with the mean, the median, and the mode to tell any story you like. So here's 2 years of price data for gizmos and gadgets. Right? Every year, both last year and this year, I sold 100,000 gizmos and 1,000 gadgets. Okay? Last year, I sold the gizmos for $10 a piece and the gadgets for $1,000 a piece. This year, I'm selling the gizmos for $8 a piece and the gadgets for $1,200 a piece. Okay? So by choosing the mean, the median, and the mode, I can make an argument that I raised my prices, lowered my prices, or left my prices the same. Okay? How do you show that you raised prices? wow, this wasn't supposed to be a stumper. But, you know, like, just be brutal. Just make an argument. You know, just like, I mean, that's a lot bigger than that, right? So I could, for example, average these two numbers. That was my average price last year. That would be $505. Okay, and whereas this year, my average price is the average of those, which would be $604. Look, I raised my prices by a lot, 20%, roughly. Okay? So that would be an argument that I raised prices. What's an argument that I lowered prices? I get to watch you be uncomfortable instead of just being uncomfortable all alone up here. Okay, so that we're doing lowered? Okay, so what mean are we going to, so you're suggesting taking the mean, what are we going to take the mean of? So that,
The quantity sold
okay, so if we take,
versus this year.
okay, so if we take 100,000 times 10 plus 1,000 times 1,000 and divide that by 101,000 and take 100,000 times 8 plus 1,000 times 1,200 and divide that by 101,000, those numbers actually work out to be the same. So that would show that I didn't change prices, which is the next question I'm going to ask. So now we already know the answer to that question. Yes?
You can say you lowered prices on 100,000 items for the load. So if that switched to only $2 and another one switched only, or you raised prices for only 1,000 items?
Sure. Okay. So the mode price went down from $10 to $8. By far, the bulk of what I sell are gizmos. The vast majority of things I sell are gizmos. The vast majority of my prices last year were $10. The vast majority this year are $8. I lowered my prices on my most popular item. Okay. Similarly, what was the median last year? The median was also 10, right? Out of 101,000 items, the median would be the price of the, you know, what is that, 50,500th item. That would be $10 last year, and that would be $8 this year. I lowered my mode price. I lowered my median price. Okay. I lowered my average if I don't pay attention to how many things I sold. If I just look at my price list and average the prices on the list, I lowered my average price. Okay. But if I look at average price per item sold, if I do a weighted average where I make a long list that has the price of each thing sold, 101,000 items on the list, and I average those 101,000 prices, I get the same value last year and this year. I didn't change my prices. Okay. Does this make sense to everybody? All right. Okay. So you can. All right. Let's look at this example. Okay. So homes in a certain area have a mean price of $400,000, but a median of only $250,000. How do you explain that? Yes?
It's B, a small percentage of very expensive homes make the mean large, but doesn't affect the median much.
Great. Okay, so it's B. B is the answer. Small percentage of expensive homes make the mean large, but because most of the homes are not that expensive, the median isn't as large. So the prices are skewed to the right. You end up with the mean being larger than the median. What's wrong with D? Isn't it true that more than half the home prices are less than 250? Well, it's as close to half as we can get while being greater than half, right? It's not. It shouldn't be more. It should be 50%. Might be 50% in a little bit, depending on how many homes there are. Okay, so B should be the right answer. Let's look at this. This is very similar to a homework problem. You pick a number. It doesn't have to be an integer. I roll a die. and I pay you $10 minus the square of the difference between the number that you picked and the number that the die lands on. Okay, so you could pick 17, and if the die rolls 1, I pay you $10 minus 16. So you pay me $6. Okay. You pick a 1, the die lands 1, I pay you $10. You pick a 1, the die lands 6, I pay you $10 minus 5. Yes, the difference between 1 and 6. What's the best number to pick to win the most money in the long run? Okay. You analyze this game, you're getting some fixed amount, and then you lose based on the distance between your guess and what happens. Okay? And you're losing as the square of the difference. Okay? So what you'd like to do is pick the number that is going to be as close as possible to what the die ends up coming up, where as close as possible means minimizing the square.
3 or 4.
Sorry?
Pick 3 or 4.
Pick 3 or 4? Well, you don't have to pick an integer. 3.5. Okay, we hear 3.5 a couple times. Okay, so you want to pick the mean of the outcomes. Okay, in this case, it's the expected value because we have a random variable. We'll get to that much, much later. But if you think that 1s are going to come up just about as often as 2s, just about as often as 3s, et cetera, then what thing is going to minimize the sum of the squared differences? It's going to be the mean of the numbers 1, 2, 3, 4, 5, 6. The mean of those numbers is 3.5. Okay, so the best thing to pick to win the most money is 3.5. What if this had said that I would pay you $10 minus the absolute value of the difference? Okay, then 3 or 4 would give you the same result. Okay, the median, you're looking at the median, but in fact, 4 is also works. Okay, I'll let you guys go. This is just a quick summary. We've got these 3 measures of location. They're all saying what's typical of a list, what's the best representation in terms of a single number, but they have different definitions of best. See you guys next time.